Welcome again, Science Warriors. It's time for another flip video here in the Atlas Academy 6th grade science course. Today we're going to be looking at the topic of changes in force and motion, focusing mainly on speed and speed time graphs. Our EQ for today is going to be what all can you do when it comes to speed. Okay, so for a little bit of instructions, be sure to read and follow all of the instructions posted on the Google Classroom post, including the page numbers. Complete your notes because you get to use them on the quiz that you will take after you finish this video. So let's do a quick review of balanced and unbalanced forces. Okay, we know that an object that's at rest has the greatest amount of potential energy. Now, of course, height can affect this. If we have a hill, an object at the top of the hill has more, and it's at rest, has more potential energy than an object at the bottom of the hill that's at rest. Then when it comes to kinetic energy, when something is in motion, we are transforming potential energy into kinetic energy, and then vice versa as something begins to slow down. So kind of the last little part to all this, all changes in motion require an input of force. So if we're going to change direction, okay, we have to apply forces. So if you ride your bike, it requires force to make you start moving. You have to pedal the pedals. You have to use a different force on your bike in order to make it turn left and turn right. And then finally, the force must be applied in order to stop your bike. You have to engage the brakes, which puts a force in the opposite direction of your forward motion. So all of these things are part of what we call balanced and unbalanced forces. Remember, balanced, usually we get no movement, but that is not every case. That's a misconception. Unbalanced forces can cause acceleration and deceleration of an object. Okay, so starting with speed, what does it describe? Well, it describes the rate of movement, okay? How fast something is going. Speed is a measurement of how long does it take in time for someone to travel a certain distance. So then how do we calculate speed? Speed is calculated with a simple equation. It is the average speed equals the total distance covered in a trip divided by the total time it took to finish that trip. This means, of course, we're going to be dividing distance by time. Now, average speed, if you ever see it written as this, we're talking about the entire trip, not a single part or a snapshot of a trip. Now, on the other hand, okay, average speed is great for the entire trip, like we just said. But if we need to figure out exactly how fast somebody was going in the beginning, middle, or end of a trip, we can then simplify that long words that were in the previous formula, and we can find out speed by taking the distance traveled in that little picture window of our trip, divided by how much time it took to go that distance, and we will find the speed of that moment in time. Okay, so let's look at an example of a speed problem. So let's say that school is 5 kilometers away, and you can get there in 15 minutes, or 1/4 of an hour. So 1/4 of an hour in a decimal form is 0.25. Your average speed, to figure that out, is going to be take the total distance, which is 5 kilometers, divide that by 0.25 hours, and you will get 20 kilometers per hour. Notice the units, just like in density. Kilometers is distance. That goes on top of our division bar. We were working in hours in this case. That goes on the bottom of your divide bar. So then our final answer has a combination of those two units. Again, just like density. This one, the final answer comes out to 20 kilometers per hour. Okay, so let's continue. At times during the trip, your bike was at a faster speed, and at times your bike was at a slower speed. Your average across the entire trip is 20 kilometers per hour. So remember, an average, you can have higher speeds and lower speeds, but because we're adding all of our speeds up and dividing it by all of the time that took, Okay, we're going to get kind of a middle of the road average of it all. So, what do these units mean? 20 kilometers per hour. This means at that speed, in 1 hour, you would travel 20 total kilometers. Okay, that's what that means. So now, how is speed measured and graphed using a distance time graph? Okay, this can be very complex, so make sure you pay attention to this section. Speed, of course, we can measure it in many different units. Okay, but it all depends on what type of distance and what kind of time are you measuring in. So for example, you can have miles per hour. We're measuring our distance in miles. Time is in hours. We have kilometers per hour. We have meters per second. We can also have feet per second. It all depends on what measurements you are taking when it comes to your distance and time. Speed graphs, though, take all these times and they tell us exactly what is happening on that trip. Okay, so the exact way something traveled, as well as make predictions. We can use these graphs to make predictions in the future if they were to continue on in a certain way. So let's take a look at those. We're going to talk about the first three in the graphic. Okay, we have these three, A, B, and C. On this graph, the y-axis is distance, the x-axis is time. In A, okay, we have a horizontal line. This means that we are having no movement. Okay, distance, okay, our distance traveled is not changing even though time continues on. This means we're at a stop. Graph B, on the other hand, okay, we are traveling forward, an upward angled slope of the line. Slope of the line just means the angle of the line. If it's going up, it's positive. So since it is also a straight line, this means that we are traveling at a constant speed. Okay, but we are moving, our distance is increasing from where we started as time also increases. Graph C, on the other hand, is a downward slope or negative sloped line. Distance is actually decreasing. We're going down the graph as time is increasing to the right. This means we are moving back towards our point of origin. So, standing still, moving forward at a constant speed, moving back to where we started at a constant speed. Now for the last three. Graph D is an arc. Okay, this arc is opened up towards the top of our graph. Kind of, if you think of this as a mouth, it is towards the top. This indicates to us that our speed is increasing over time. So we're starting at one speed, then we're getting faster and faster and faster. This indicates acceleration. Graph E is the exact opposite. The mouth is facing downward. Therefore, our speed is decreasing. Okay, the amount of distance we're covering for every second or every hour is getting less. So this is a deceleration graph. Now, graph letter F is an example of what you can see when you compare two different racers or two different trips. Basically, this is the same as graph B in that we are moving at a constant speed forward, but because the slope of the line right here is not as steep as graph B, this means that our speed that this person is traveling is less than the person who is doing the trip here in graph B. Okay, these 6 examples and then looking at the slope or angle of these lines is going to be very important for determining what is happening if you are ever given a distance time graph. Okay, these are very key. But all right, everybody, that's going to be it. This is the very basic beginnings. There's not a lot of practice, but we will be doing a lot of practice in class as well as another lab. So please have these notes ready by the due date so that you will have all the knowledge you need in order to complete your tasks in class as quickly as possible so that we can move on and continue our dive into force and motion. Well, Science Warriors, that's going to be it. Really do appreciate it. You guys have a great night, and I'll see you in class.